So now you've seen the definition of a derivative, and you've seen it in action. We've done some kind of basic questions. And you probably noticed, as often is the case with math definitions, it certainly seems, it's not the easiest thing in the world to work with. So we're going to do, again, what we often do in math, once we've got this definition, that we didn't have a whole lot of choice in. Right? The definition was based on things we already knew. It was based on the definition of a limit, and it was based on the definition of the slope of a line, things that we really weren't in a position to change. So now what we're going to do is we're going to look for easier ways to find the derivative of functions in certain cases, right, with certain functions. And one of the nice things about the derivative is there's almost always going to be a formula or a procedure of some kind that we can use to find the derivative of a function. Okay, so here's where we're going to start. We've got some properties. And these probably look familiar, right? Because these properties are very similar to properties we already saw when we were talking about limits. For example, this first one says if you have the derivative of a constant times a function, you can just take that constant and bring it outside. Right? And I'm not going to really belabor the point of proving these things because they all really follow directly from the corresponding limit properties. For example, let's take a look just at this first one here. The derivative with respect to x of c times f is the limit h approaches 0, c f of x plus h minus c f of x all over h. But now look, both of these terms in the numerator have this c in common, right? So let's factor that out. This is the limit h approaches 0 of c f of x plus h minus f of x all over h. But now I'm going to use the limit property. We have a limit property that says you can bring that constant out in front. So this is c times the limit h approaches 0, f of x plus h minus f of x all over h. But this right here, that's just the derivative of f. Right? So this is c times the derivative with respect to x of f. And the other two work exactly the same way. Right? They're all based directly on the corresponding limit property. All right, so let's start looking at some specific limits. And I'm building up to something here. Right? I'm building up to something. And in the back of your mind, I want you to keep this idea in your head. What's the derivative of a polynomial? Right? That's where I'm really kind of going with this. Okay, so right now, I want to show that the derivative of a constant, right, f of x equals c, the derivative of a constant is 0. All right, and this is easy enough to show. We'll use the definition here. F prime of x is the limit h approaches 0, f of x plus h minus f of x all over h. Okay, f of x plus h is c. F of x is also c, right? F is always c. It's a constant. Well, this is the limit h approaches 0 of 0 over h, which is the limit as h approaches 0 of 0, which, sure enough, just like I claimed, is 0. Okay, so what if we have something like this thing here? What if we have something like x to the n? For example, x squared, x to the 5th, x to the 7th. Then what? Then what's the derivative? Well, my formula here says we can actually do this really easily. And let me do this for comparison. Let me put f of x up here. This is the original function. Right? So what my rule is saying is we take the exponent and we bring it down in front and we reduce the exponent by 1. And that's all it takes. That gives me the derivative of this thing. So we're going to look at a bunch of examples of this before we're done with this lecture. But let's just look at one quick one here just to see this in action. Suppose we have f of x equals x to the fifth. What is f prime of x? Well, my formula here says you take the exponent, you bring it out in front. So this is going to be 5x, and you reduce the exponent by 1. 5 minus 1 is 4. And that's it. Right? That's all there is to differentiating these things. Okay, so now we can really do some cool stuff. Now we know everything we need to know to find the derivative of any polynomial. Right? So let's look at some examples. Right? Very basic one to begin with. All right. Now this is really close to what I did before, right? But it's got a -3 out in front. Well, remember our very first derivative rule. It says you can kind of ignore a constant out in front, find the derivative of the actual function part, the part that actually has the variables in it, and then just multiply the result by that constant. All right. So in other words, f prime of x is 3 times the derivative of x to the fifth. Excuse me, there's a minus sign there. -3. And that is -3. Let's see, we already saw this one, right? You bring the 5 down in front, 5x, and you reduce the exponent by 1. So that's 5x to the fourth. Now just clean it up. Multiply the -3 and the 5. This is -15x to the fourth. And that's it. Right, there's my derivative. Right, so let's try something even bigger. Right, what's the derivative of this thing? Well, f prime of x equals. Now I'm going to use the first all three rules really. I'm going to take the derivative of the individual pieces. Right, remember rule number 2 and 3 said the derivative of a sum is just the sum of the derivatives. So I'm going to do the derivative of -4x to the 12th plus the derivative of 6x to the third plus the derivative of -4x plus the derivative of 2. All right, so what do we get then? Right, you bring the exponent down in front. -4 times 12 is -48. Reduce the exponent by 1, x to the 11th. Plus, bring the exponent out in front. 6 times 3 is 18, x squared. Reduce the exponent by 1. Plus, now look, this one, it's a little different. It's a little unusual in the end, but I'm going to follow the same pattern. The exponent here is a 1. I'm going to multiply -4 by 1. That's -4. And I'm going to reduce the exponent by 1. 1 minus 1 is 0. Plus the derivative of 2. Well, we saw earlier, right, a couple slides back, the derivative of a constant is 0. Now we're just going to do a little cleanup. -48 x to the 11th plus 18x squared minus 4, right? Because x to the 0 power, anything to the 0 power, except for 0, of course, anything else to the 0 power is 1. And there's my derivative. All right, so how about this thing? Now here we have to be careful. This is a bad time to start trying to be creative. Okay, we know how to find the derivative of a polynomial, and that's awesome, but this is not a polynomial. Right? A polynomial is x to a power, not 3x plus 1 to a power. But look, I can still do this. I'm just going to have to multiply it out first. This is f of x equals 3x plus 1 times 3x plus 1. Then I can multiply this out. 9x squared plus 6x plus 1. And now I can take the derivative. Right? F prime of x equals, let's see, 9 times 2 is 18. Reduce the exponent by 1. X squared becomes x to the first. Let's see, the exponent here is 1, right? 6 times 1 is 6. Reduce the exponent by 1, it becomes 0, and x to the 0 is 1, plus, well, 0, right? The derivative of a constant, so I really don't need that on the end. And that's my answer, 18x plus 6. Okay, so let me give you one, right? Take a look at this one. See if you can work this one out real quick. Hopefully these are starting to come. These start to come quickly, pretty fast. All right, so let's see. I want f prime of x. 18 times 3 is 54, x to the 17th, plus 7 times 4 is 28, x to the 6th. Minus 4 times 3 is minus 12x squared, plus 2x to the 0, which is 1, minus 0. And that's it. It really is that fast, right? So now we've got, with these great new tools, we can find the derivative of a polynomial really quickly. All right, what about this guy? Not a polynomial, but look, if you look back, to when we talked about the formula, you'll notice I said x to the n where n is a real number. That n doesn't have to be an integer, right? I can do this with any exponent. So I'm going to rewrite this. I'm going to make this y equals 3x to the 1/2. Right? I'm going to go to a fractional exponent because now it's a number. When the exponent is a number, I can use my rule. Y prime, using y this time, right, equals 3 times, bring the exponent out in front, 1/2 times x to the 1/2 minus 1. So this is 3/2 x to the negative 1/2. And now let's say I'm going to clean up a little bit. This is 3 over 2 x to the 1/2, which is 3 over 2 times the square root of x, and that's it. I'm done. There's my derivative. Really quick with this great power rule. Okay, so how about this thing? You can pause if you like, right? Try and work this out, see what you come up with. Then we'll do it together. So I'm going to do the same thing I did before. I'm going to replace this cube root of x with x to the 1/3 times x minus 1. And then let's see. Now I gotta distribute, right? I'm going to distribute the x to the 1/3 into the parentheses. This turns into y equals negative x. Remember what we do with exponents now? X to the 1/3 times x to the 1st. We'll add the exponent. So this is x to the 1/3 plus 1 plus x to the 1/3. All right, so let's see. That's negative x to the 4/3 plus x to the 1/3. And now I'm going to do the derivative. Y prime equals negative 4/3. I bring the exponent out in front. X to the 4/3 minus 1 plus 1/3 x to the 1/3 minus 1. All right, now let's see. Let's clean these exponents up. This is negative 4/3 x to the 1/3 plus 1/3 x to the negative 2/3. Okay. So here's what I'm going to do. I want to continue with this. I want to simplify this even further. Right? And what I want to do is combine these into one fraction. So I'm going to do a little factoring here. Right? And I want you to think about what happens as I do this. I'm going to factor out a 1/3, and I'm going to factor out an x to the negative 2/3. And that's maybe not a little intuitive to you right off the bat, but watch. Right, let's see what happens. What's left from this first term? Well, I still have the minus 4 that's left behind. All right, and the x part is going to be x to the 1st. And I want you to think about that. Right? Try distributing this back into here. If you distribute this back in, x to the negative 2/3 times x to the first, let me write it for you, x to the negative 2/3 times x to the first is x to the negative 2/3 plus 1, which is x to the 1/3, which is where I started from. Right now, what's left here? Well, I took really the whole thing out. I took the 1/3 out, and I took the x to the negative 2/3 out. So all that's left here is 1. Right now, I can get my final answer. Y prime equals negative 4x plus 1 over 3x to the 2/3, and that's my final result. I really want you to take a minute, go back and think through that factoring step if you need to. This is a technique we're going to come back to later on in the class when we start talking about doing applications with these derivatives. Okay, how about this thing? Yeah, I know, hard left turn, right? Big change of direction here. How can we find the derivative of trig functions? Well, we don't have a whole lot of options at this point. It's not a polynomial, so I can't use my power rule. And all I have left is the definition. All right, so let's go to the definition. But before we do that, I want to remind you of a couple of things. A couple of things we've seen already. The limit as theta approaches 0 of sine theta over theta is 1, and the limit as theta approaches 0 of cosine theta minus 1 over theta is equal to 0. All right, hold on to those. We're going to need them before we get to the end here. All right, so I want to find y prime. Y prime is the limit h approaches 0 sine theta plus h minus sine of theta all over h. Okay, so I'm going to do kind of the obvious thing here, right? With that sine theta plus h, I'm going to bring out my sine formula, and I'm going to rewrite that using the sine addition formula. So this becomes the limit h approaches 0 of sine theta cosine h plus cosine theta sine h minus sine theta all over h. Okay, now I'm gonna do a little rearranging, right? I'm gonna bring this sine over here. So this is the limit as h approaches 0 sine theta cosine h minus sine theta. You see why I kind of put it over there, right? I'm looking ahead. I'm thinking maybe I can do some factoring with that part. Plus cosine theta sine h all over h. Okay, now I'm going to split this up, right? I'm going to make this the limit h approaches 0, and I am going to do that. I'm going to factor out the sine theta. Let's bring out that sine theta times cosine h minus 1 over h. And I'm going to split this, right? I'm going to do plus the limit h approaches 0 cosine theta sine h. Okay, now here comes kind of an interesting step. Notice that sine theta doesn't have an h in it, right? Because it doesn't have an h in it, it's not affected by that whole h approaches 0 thing. I can treat it just like it was a constant and bring it out in front. So this is the limit h approaches, whoops, excuse me, I got to bring it out in front. This is sine theta, limit h approaches 0, cosine h minus 1 over h, plus, and I'm going to do the same thing here with the cosine. that cosine of theta doesn't have an h in it. So I'm going to bring it out in front. Cosine theta. Whoa, I'm sorry. I lost the over h here. Cosine theta, limit, h approaches 0, sine h over h. Now I'm going to use my two identities over here. This limit is 0. So that's sine theta times 0 plus cosine theta, and this limit is 1. And there's my answer. Right? This goes away, and I'm left with cosine of theta. All right, so I want you to think about what I just did here, right? Because with that y prime up there, it got hidden a little. The derivative with respect to theta of sine theta is cosine of theta. Right, and I've got one more here. Obviously, if we would do the sine, we want to do the cosine, right? Well, what is the derivative of the cosine of theta? I'm just going to give you this one. Y prime equals minus sine of theta. And I'm going to leave you to think about that one, right? See if you can't work that one out on your own. And it's going to use a very similar process to what we just did with the sine function. Okay, so we've got some great tools now. Right? We know how to do the derivative of a sum and a difference. We know how to do the derivative of a constant times a function. We can handle any polynomial. We can really handle anything that just has x's with exponents, even if they're not integers. And we've got our two basic trig functions down. Now, one thing you might have noticed that we didn't talk about, you might have expected, right? We didn't talk about the derivative of a product. Okay. There's a reason we didn't. This is actually a little trickier. This is not the derivative of f times the derivative of g. You cannot do this with a product. You also can't do it with a quotient. It doesn't work. Okay. We can do it. We've got some formulas. They're called the product rule and the quotient rule, but they are a little more complicated. All right, so that's what we're going to take a look at in the next lecture.